invitation to be here. It's great to come up to Sydney, and it's a nice change from quiet Canberra. Okay, so today or tonight I'm going to talk about some work we've been doing on climate change effects on Australian passerines. We've been doing this work for about 10 years now. And much of what I'm going to talk to you about tonight is about arid zone birds. That's because they're particularly vulnerable to climate change. And they also act as an early warning system, if you like, to see what's coming to the temperate zone. Okay, so it's technology.
So everybody here, all right?
Yes, all right. Okay. Okay, so I'll just start out quickly by talking a bit about how the climate's changed, just as a starting point. Okay, so the planet is warming at a very rapid rate. We have these 3 global climate stations around the world, and they're all showing the similar pattern. We've seen this rapid increase in mean temperatures across the globe since about 1900. So we've seen more than a 1 degree warming now. Most of that's occurred since 1910, or since 1910 rather, most of that since about 1950. From about 1970, it's ongoing. There's been this doubling of warming compared to the last 100-year trend. Okay, so in Australia, we're seeing the same pattern. At present, we're approaching a 1.5 degree increase in mean temperature since 1900.
Just when you turn away from the audience, your voice is a bit muffled.
Is it?
So
Okay.
you can use the microphone there. That's only going for the video. It's going through the system.
Oh, oh, this is linked to that. Okay, sure. All right. So this again shows the same sort of pattern that we're seeing, particularly since about 1970, this rapid increase in warming compared to the temperature anomaly, which is the data for the last 1960 to 1990. All right, so the warming is consistent across the land surface of Australia. So these warm colours here represent an increase in temperatures, and the blue colours, the colder colours, a decrease in temperature. And clearly there's no blue there, so the whole of the terrestrial surface is warming. This is now outdated. As I say, we're approaching 1.5 degrees now. That's wrong way. Okay. So this rise in mean temperatures is also accompanied by an increase in the frequency and intensity of heat waves. So this is characterised here as the numbers of days in each year that have seen temperatures above 35 degrees. You can see that we've seen a doubling since 1960 to about 2010 in the numbers of these hot extreme days. And of course, since 2010, we've seen many more. So it continues to rise at an alarming rate. Oops. Okay. In contrast to the mean temperature change, we're seeing much more variation in rainfall patterns. So in Northern Australia, we're seeing floods, much more heavier rain. But in Southern Australia, we tend to see these drying events. So it's much more variable than temperature. So the question we've been trying to address is how is this affecting our birds? So the first step, we wanted to see how the climate's actually changing on the distributions of individual birds. Is it showing these same sorts of trends? So we looked at the distributions of 93 species of Australian passerine, both Boydea. This is this super family of Australian birds. This the berry wrens and grass wrens, parlotes, honey eaters, hornbills, warblers and allies, and the bristlebirds and parlotes. So there's about a third of our passerines, and we looked at how the climate has changed in each of their distributions over the last 50 years. So the way we did this is, just shows the distribution of each species. Ignore those black crosses, they're for something else. But for each cell in this species range, we extracted the data, the climate data for the last 50 years. And then we are using based on the bomb weather data, and then we plotted it over time. So what you see is this is the change, or this is the year, mean temperature, annual mean temperature for each year. Each line represents an individual species. And what was extraordinary to me that 92 of these 93 distributions, we're seeing an increase in temperature across the birds in this superfamily. I hadn't quite expected to see this consistent increase in temperature. I thought we'd see much more variation. But when you look at the maps of Australia, then it's not surprising, but it's sort of a stunning moment to me to see it at this level. So by contrast, as you might expect from the Australian pattern, the annual rainfall is much more variable. Okay, so what does this mean? What are the impacts of this changing climate on our avifauna? That's the question we're posing. Well, obviously one component of climate change that we're seeing more frequently now is these catastrophic heat waves. They're massive mortality events during extremes. This is an example here of budgerigars that there was a mass dive in 2017 when temperatures approached about 45 degrees for a couple of days running. So these sorts of events are becoming much more common. But it's surprising that we actually know relatively little about how temperatures actually affect survival and reproduction of our birds. So the sorts of questions we're interested in trying to answer are, well, which species and individuals are affected? And at what temperature thresholds do we see changes in their body condition, their weight loss, for example, or their survival? And how does that affect reproduction? So that was the sort of background to the work that I'm going to talk about now. So it made sense then, if we're interested in this particular topic, to work in the arid zone, arid and semi-arid zone. It comprises, of course, 70% of our land surface, so it's very important in terms of impacts on biodiversity. So this is where we've been working. So arid zone birds are particularly vulnerable to climate change because they already live close to their physiological limits. They experience thermal stress, both hot and cold, and that's in conditions in which resources are unpredictable. So resources come and go with rain. So they're endotherms, of course, birds and mammals are endotherms, which means they must defend their body temperature against these changes in their local environment in terms of the weather conditions they experience. And if they don't do that, they're going to die. So body temperatures of 46 degrees are lethal for most birds. So when you think about the hot end of the temperature scale, this creates this conflict between the need to conserve water and avoid dehydration in these hot conditions, but yet they're reliant on evaporative cooling. So they must lose water to keep their bodies cool when air temperatures exceed about 40 degrees. So they really are facing a challenge. So I'll just show some slides about the ways in which birds can, before they experience a physiological cost, they tend to modify their behaviour to avoid heat stress. And this includes changes in posture. So this bird is sort of on a cool morning fluffed up. It's got trapping air in its feathers to stay warm. But as it gets hotter, it flattens out its plumage to get rid of that trapped air. And it pops its wings out just slightly. And that opens up the window, the thermal window, where the feathers are not so dense and it loses water. It loses heat this way. So it dissipates heat. As the temperatures increase, they tend to start really drooping their wings, and you can see this quite obviously. And as it gets hotter still, they'll move to higher perches to try and catch the wind. So they're actually windsurfing up there as a way of losing heat through convection. So that's all well and good up to about 40 degrees. But once air temperatures reach about body temperature, they need to use evaporative water loss to stay cool. It's the only option they've got. So they pant, which increases water loss and increases dehydration risk. So once they're exposed to long periods of these high temperatures, they really are at risk of lethal dehydration. So these are some photos of dehydrated birds that we took. These are Jackie Winters that we went out the day after temperatures had reached 47 degrees. And this is what the birds look like. They've obviously got sort of shrunken eyes. They're very lethargic. They're looking quite ill. So they can survive 47 degrees, but it clearly, it costs them. Okay, so how are rising temperatures affecting Arizona species? We chose the Jackie Winter to sort of undertake a case study. Now, of course, you all know it's an Australian robin. Now, it's sedentary at the site we studied them, so they're not going to move off, so we can tell whether they're there or not, whether they're likely to have died in heat waves, for example. So they're sedentary, they're an insectivore. Now, they don't drink free water. All the water they gain is from their diet, from the insects. Now, they weigh 12 to 16 grams. The sexes are monochromatic, so they don't look different, and they're about the same size as well. So we undertook this study at Calfram Station in Renmark. So this is Adelaide, so up in the dry country. It's right on the edge of the arid zone. It's dry there. You get about 200 mils of rain each year, and it gets hot in summer. You can get up to sort of 49, 50 degrees. So that's me. So Calfram is a wonderful place. It's a semi-arid mallee woodland. It's adjoins Taylorville and Glue Pot stations and Dangali Nature Reserve. So in total, it's the largest single tract of this semi-arid mallee woodland in the world. It's greater than 1 million hectares, and it has really high conservation value. So it was a great place to work from a birding point of view. So the way we undertook this study was we worked out in this area here. You can see the rolling dunes. It's all dune country there. So we captured and colour banded 40 breeding groups of birds, so about 90 individuals. So you can see each of them has got a set of coloured leg bands, so we can identify every individual. And that means we can follow their fates across time. We can follow every reproductive attempt they make. We can band their chicks when they're in the nest, and we can follow their fates over time. So we understand then who lives, who dies, in what conditions, how successful is reproduction, and under what conditions do they face life-threatening weather, for example. So we monitor survival and reproduction in each year. So now a subset of these birds, we trained to stand on an electronic balance so we could weigh them each day. So this is a Jackie Winter coming in to be fed. It gets a mealworm if it stands on the scale. Mealworm weighs about 0.2 of a gram, so that's really only about 2% of its daily food intake. So we weigh them every day, and we can look then at how their body mass changes in response to weather conditions or parental investment in their chicks, or all these sorts of interesting biological states. Now, it takes quite a lot of investment to do that. This is Linda Sharp, who trained these birds. She's worked on all sorts of animals in Africa mainly, but she's a real bird whisperer. It's not a great photo, but she's at the scale there. And I was just going to show you a bit of footage about how this actually works. So the birds come in on call. We get the weight, and then that's it for the day. Right. So they're not the only birds that habituate out there. So this chestnut quail thrush will actually have got used to mealworms. We didn't actually set out to feed these birds, and we didn't do it much, but they'd come up to you, especially these quail thrush, which amazed me because they're often birds that really take off and don't like people, but if you've got a bag of mealworms, they like you. They'll come right up and stare right up in your face. So that was a lot of fun as well. Okay, so the first part of the study was looking at responses to heat waves. How does their body weight change when they're subject to heat waves? So in January 2019, we experienced the hottest month ever recorded at Calprum. Temperatures were 4.2 degrees above average, and that actually represents the same temperature increase predicted for the region for 2090. So you're looking into the future in some way. So this is just the birds that we were weighing, and each of these is a day. So we mark W is we've got a weight, WP is a very good weight, and there's all sorts of we didn't get a weight. This bird was observed, but it wouldn't get on the scale. But basically, what it's showing here is that we really do weigh them every day if we possibly can. We had about 5 weeks of heat waves, and we weighed them right through and then up the other side. These pink bars represent temperatures that were above 40 degrees, and these hot pink is temperatures above 45. So you can see that the conditions were really hot right through this period. So this is what the data, okay, so then we have a weather station set up and we're logging the weather every 15 minutes. So we get really fine scale information about how body weight changes across the course of the day, or between days in this case. And this is another one of our birds. So this is mass change, the percentage of body weight they lose or gain in relationship to maximum temperature they've experienced. So you can see that this is 0, so they maintain their weight, put on weight above here, and they lose it below here. So when it's cold, they lose weight, and then they're sort of very happy between 25 and 40 degrees roughly. But once it gets hotter than 42 degrees, they start to lose weight quite dramatically. And at temperatures above 42 degrees, they lose about 2% of their body mass each day. When it's 45 degrees, they lose about 2.6% of their body mass each day. But it's not just the maximum temperature they experience, it's also the duration of the heat exposure that's also recorded. This again changing body mass, but this is exposure time in minutes. So this blue line is for temperatures above 40, 42 and 44. So we can then calculate where these lines cross the 0. The birds can tolerate about 140 minutes of temperatures above 40 degrees before they start to lose weight. But by the time it's 44 degrees, they can only maintain their body weight for 25 minutes. So it really is quite a dramatic impact that these heat waves can have. And on the hottest days out there, birds are actually exposed to up to 10 hours of temperatures above 40 degrees. So it's a miracle that they're coping, seems to me. So during this period of 5 weeks, we saw that mortality increased almost threefold. 20% of the adult population died in this December-January heat wave. And that's compared to 6% of deaths in the previous 2 months. Now, because we know exactly where every bird lives, we go and check after heat waves, we have to search those territories 3 times in a row to be sure the bird's gone. Because they don't leave their territories and go elsewhere, they're resident for the rest of their lives, we can be reasonably confident that it's the heat waves that are killing them. Of the fledglings that had left the nest by then, 53% of those individuals died in those heat waves, compared with about 35% in the prior to December 1. So fledglings die a lot, especially when they're young, but that's still quite an increase, 20% increase in deaths over that period. Now in December 2019, we had another horrific year, and we lost 28% of adults died within 24 hours of temperatures reaching 49 degrees. So it's really staggering effects on these populations. But you know what was the most surprising result we thought was that actually when you think about it, these birds are quite resilient to these heat waves. 3/4 of those birds survive 49 degrees. So the question is, how do they do it? What makes them resilient? So based on lab studies of physiology, they estimate that a similar sized bird, we would expect, based on those lab studies, we'd expect Jackie Winters to lose about 20% of their body weight on an average day above 45 degrees. That's what you would expect from the physiology in the lab. But clearly that's not happening. And they should all be dead because lethal limit in terms of mass loss is between 11 to 18%. So how are they doing this? How are they not losing 20%? What's wrong with the lab studies? Well, the answer is that they actually regain weight between these heat-wave events. So this is just to show you the pattern there. So again, body mass change, and this is every day. This is the maximum temperature, these bars. So it's that's purple lines 40 degrees and 45 in the red. So these days we're above 45, these days we're above 40. And you can see this is just one Jackie Winter, just to show you how quickly they respond to changes in temperature. So they go down, weight loss when temperatures rise above 40, and then they go up when temperatures become cooler again, and then they go down, up, down, up, down, up, down, up, down. So they're responding in this 24-hour time frame, much faster than we had imagined was possible. What was even more surprising, that these survivors regained their pre-heat wave weights within 2 weeks after the last heat wave. So this is before the heat waves began, after a week, after 2 weeks, and then 2 weeks after the last heat wave, they regained their body mass. So they're extraordinary. So how is it that some individuals survive but not others? Well, we're working on this question at the moment, but it seems to us that it's probably they use behavioural thermoregulation and they use habitat refuges to survive these periods. They go down to the ground. So we've been out there studying them, following them around, doing structured behavioural watches when temperatures rise up to about 45, and we characterise what they do and when they do it in terms of temperature. So when it gets to about 38 degrees, as the day warms, they do this business of going higher, surf the breeze, but as soon as it's 38 degrees, they go to ground. And where they go is into the bases of these old mallees. And this is a chestnut rump hornbill. Lots of birds out there do the same. And they stay in these refuge sites, which are cooler than air temperature, and they'll stay there until temperatures drop down to 38 degrees, and then they come out. But it seems to us that this is how they're doing it. They're seeking refuge. But the key, or the concern here, is that not all territories have these good quality refuge trees. And we'll talk about that a bit later. So we know that these heat waves involve mass loss and mortality. But we also know for those that survive, heat exposure can cause organ damage. There's people at Adelaide Uni working on this, and they've found that you get kidney damage, for example, when you're exposed to temperatures above 35 degrees for consecutive hours. So we're still doing some analysis to look at how you might perform after you've been exposed to heat waves. So what are the carryover costs of this mass loss and organ damage on molt, survival in winter, and reproduction in the following year? They're the sorts of questions we're looking at now. So if we now move to reproduction to look at how the birds are going in response to heat when they're reproducing. So they nest between August and September. They have these open nests in the forks of branches. They have two chicks, or they lay 2 eggs, hatch 2 chicks. These are getting close to fletching. These are about day 14 since they hatch. So we're particularly interested in what's going on here because we've seen a 5-fold increase in the numbers of days above 42 degrees in the breeding season since the 1960s. So we're getting this massive increase. So just in this, during the breeding season, we're just looking at November, December here, because that's mainly when they have eggs and chicks in the nest. So it's becoming really hot. So how they going? So we did, the questions we're really interested in, how does it affect parental workloads? Is it costly to rear chicks in the heat? We think it probably is. And how does this heat affect hatching and fledging success? So how's reproduction going in terms of numbers when it's hot? So we spent a lot of time videoing nests. So we set up these cameras. We set them up during both the incubation and the nestling period because we wanted to measure the costs on chicks as well as eggs and on parents during the different phases of reproduction. We've got data at the moment for about 100 nests and well over 1,000 hours of footage. This is where honour students come in. They tend to get them onto these projects and they never want to look at a video and we're getting them. And we've got a new student this year who has been putting eye buttons into nests after those nests are vacated, because we're interested in what are the temperatures at the nest compared to the air temperature, because if those nests are exposed to the sun, they're actually much hotter than air temperatures suggest. So she's busy analysing her data right now. So during incubation, this is just to show you the nests again. They're quite cryptic and they're quite exposed. There's a bird sitting there. So you can imagine the heat load on that bird on a 45-degree day is extraordinary. Okay, so heat increases parental effort. That seems to be clear. Females who do most of the work at the nest, she does all the incubation and brooding, their effort doubles. So they double their nest attendance between 28 and 40 degrees air temperature. So what happens is they switch from incubating eggs, like you've just seen, to shading them. And they've got to shade them to keep them cool. And if the sun gets on those eggs, they're dead very quickly. So this is, she sits there with the sun on her for a long period of the day. So where she actually builds the nest is actually critical for her own survival as well as those of the offspring. When it gets real, she does all of the shading except when it gets really hot, and the male will kick in and help a bit, usually when temperatures are up around above 40 degrees. And he comes to the nest and he feeds her while she shades and incubates. So this is just to show you the proportion of time that the female spends shading the nest as maximum temperatures increase. So she doesn't shade at all till it gets to about 25 degrees. And then she spends an enormous amount of time shading those eggs, up to almost 100%, up to about 99% of time shading eggs in nests that are exposed on really hot temperatures. Once she gets to here, she abandons because it's too hot, but we'll get to that in a minute. So these egg shading females, they end up panting to avoid hypothermia. This is the proportion of time they spend panting. You can see when temperatures get to about 35, she sits on the nest and she's panting. She's spending almost 100% of her time panting and she's losing water, and this increases her dehydration risk. So breeding in the heat seems to be very costly, particularly for females. This is exacerbated by the fact that the male feeds the female much less when it's hot. So he feeds at a high rate when it's up to about between 10 and 20 degrees, but after that, his rate of feeding declines. He doesn't need to feed her as much because she's not using as much energy to stay warm. But when it gets to about 38 degrees, he never feeds the female on the nest. So her, she is really at risk of dehydration. So if we look at hatching success for these nests, this is the percentage of nests that fail to hatch in relation to air temperature. So less than 35 degrees, we have almost 100%, not quite. But as temperatures rise, hatching success declines. So above 35, we get a decline in hatching success, and egg mortality is complete. 100% of eggs die when temperatures reach 42. That's about 42.5 degrees. So all eggs die at around the mid-40s. So if we look at the nestling period, there's some chicks. They do this weird heat dissipation behaviour. They stand up and stretch their necks. I think they're losing heat through convection. This feather tract doesn't come in until very late in the bird's development, which is quite unusual for young chicks. So again, we're seeing the same sort of pattern. The females switch from brooding to shading eggs in the low 30s, low 30 degrees. The parents stop feeding the chicks, both male and female feed chicks, and that stops at about 38 degrees again. And then parents abandon the nest entirely when the temperatures reach the mid-40s, and chick mortality is 100% when temperatures exceed 43 degrees. So overall, when you look at reproduction in total, it's the early arrival of heat waves that are problematic, and they can lead to a 50% reduction in reproductive success between years. So birds, I mean, in the arid zone, they get historically they've had these heat waves and the chicks will die in the nest, but the issue here is that we're seeing greater frequency of these heat waves, and they're coming earlier. So when the birds are at peak breeding time, they're hit with a heat wave, everything dies. And if it happens in December, they tend to stop breeding and don't start again. We had a case in November where we got a 46-degree day. Everything died, they re-nested. 2 weeks later, it was 49. Again, that killed all the eggs and chicks, and they stopped breeding altogether. So in January 2020, we're not long back now, we had 2 days at 43 degrees, but that didn't happen until January, and it's been a much milder year. So reproduction just boomed. But how often are we going to get those mild years? That's really the question. Parents lose weight by the end of the nestling period, particularly females. And we had 4 cases where parents died trying to shade their eggs in 49 degrees. So these heat waves have got effects on both offspring and birds. We think habitat quality, again, is very important. There's little protection. So where they build their nests, the quality of the habitat they live in is probably critical for both survival of offspring and for themselves. So we still need to assess fledgling survival and recruitment, how many of them survive once they leave the nest. And we're doing this sort of analysis now. So that's the sort of case study. It gives us a picture of what's going on, what temperature thresholds are critical for survival. But now we change track and I want to look at the bigger picture. So are Jackie Winters an aberrant species, or is this a pattern that we're going to see across the arid and semi-arid zones? So to ask this question, we wanted to look at the effects of weather on survival, not reproduction, just survival, and to see whether it's common that these birds are dying when they're exposed to these high temperatures. So to do this, I've joined forces with a number of bird banding groups from around Australia. These are people that have been working at the same sites for 30 years or so, 20, 30, 40 years. They go out and they catch and band birds, and they recatch the same individuals over time. But they have these massive fantastic data sets where you can look at survival of individual birds in relation to temperature variation. So this is us working out in the Great Sandy Desert in WA. This group of banders go out every 2 years. Missed one. Okay, but the data sets I'm going to talk about now are from the Charcoal Tank Nature Reserve site and the Wedding Mountains Reserve. So these sites have been run by Mark Clayton and Richard Allen at Wedding. They've been operating these sites since 1986, and they had about 30,000 captures at each site over those 35 years. So it's Western New South Wales on the west side of the Great Divide. Sites are centred out. So the mean, just shows how the number of days above 38 degrees has increased since 1990. So this is wind, so it's still in, these hot days are increasing. This is charcoal, and they're increasing at a higher rate. So it's getting hotter at both sites. So we looked at survival and climate for 36 species, common species that they've been catching. So hornbills, honeyeaters, pardalotes, finches, whistlers, robins and babbler. And we then used this data to predict survival probability as a function of weather. We're interested in temperature extremes. So we looked at survival probability in the summer in response to the numbers of days above 38 degrees. And we see that survival declines in hotter summers. This is across 35 years. So survival is about 92% when there's no days above 38, and it drops to about 42% when you get 30 days above 38. We also looked at cold in winter, and again we're seeing a reduction in survival in colder winters. 88% survival drops to 56% when we get cold winters with 44 days of sub-zero temperatures. If you look at compare the reduction in survival lower than 80%, you can see that they're better at handling the cold. So it takes 20 days below zero before you see a decline in survival below 80, where it's only 10 days for days above 38. So it doesn't look like they're coping with the heat that well. So we then use that data, the predictions for survival, to look at what's going to happen by the end of the century. So to 2100, this is the data for winter. So we can see that the numbers of cold days are declining, and they're expected to be down here by 2100, while the numbers of hot days are increasing to 2100. So the question we then posed was, let's have a look at that. Okay, so what's going to happen as the winters warm? In winter, we expect to see an increase in survival, which is what we see. We get the change upward survival as a result of warmer winters. But in summer, we're going to see a reduction in survival as the summer's warm. So the question is, can this increase in survival in winter counteract the reduction in survival in summer? And the answer appears to be no. Annual survival by 2100 will be about 20% lower than it currently is. And that's across these 36 species of birds. So it appears that it's a general phenomenon. These heat waves are probably having broad scale effects across species. So what do we do? What's the answer? Is there an answer? Of course, it would be naive to say it's not going to involve populations in decline and perhaps some species going extinct. So what do we do in the face of a 3-degree increase, which is what's now predicted to the end of the century? Well, about the only thing I think we can say is that the quality of habitat is absolutely critical to survival in these hot areas. So I said Jackie Winters go to ground. This is just some fairly poor quality pictures. This is on a 45-degree day, but you can just see that we have this grey shrike thrush finding a hole. It's in there for about 8 hours. This cloud thrush actually digs, they use these pits and they spread themselves out in the cold sand. And again, there's a chestnut monk. So these sites are really critical for survival. But the issue is that these sites only occur in big mallees. You don't get the formation of these hollows in young trees. And that just shows you young trees come back after fire. This is the fire map for our study site. These red dots are the location that we've seen birds in 1 year. So the fire scars, 1978 is the worst in the dark. Oh no, that's 1974, sorry. And then we've got these 78 scars. And then this is old unburnt country. And you can see that the birds are not really using these burnt areas. And we think it's possible that they have once been there, but they may have died in heat waves because they do not have thermal refuges, because the trees aren't large enough to provide this life-saving shelter. That's the work we're working on at the moment. But I guess the overall message is habitat quality is critical. So any sort of environmental offsets, we clear one sort of area of land in exchange for another area needs to be really examined in these kinds of areas, in the arid zone, because one type of habitat or the quality of habitat is not necessarily the same, and therefore they offer different prospects for survival as the climate warms. So these are the various people, that lots of people have been involved in this study, particularly Linda Sharp, who's a research fellow on the ground who ran much of this work, oversaw it. She, with Belinda and Marina, who worked each year, and our students, given various volunteers who come in to help with some of the hot work. We can only be out for 2 hours at a time. And lastly, other thanks, of course, to the bird banders, Mark and Richard, to Australian Landscape Trust, who own Calcrum Station and manage it for its biodiversity values, to the Neelys, the ecologists, to Robertson and Peter Power. Tim Bonnet at ANU did the modelling for the survival. And of course, the funding is pretty important to keep these going, and sadly we've run out of funding, so we're looking for more. But the Australian Research Council, Northern Wetland, South Australian and Canberra Ornithologist Group kindly provided funding that allowed us to do this work. So thanks for listening.
So we're happy to take some questions.
Yeah, sure.
Okay, well, can we put some lights on, please? Dick, so I can't really see anybody. Very interesting, if rather depressing, study. It's, you know, I mean, you're documenting decline, and while it's important to do that, because, you know, a lot of people talk about this and everyone says, oh, it must be happening, but you've actually documented that it is happening, and it's happening at an accelerating rate.
That's right. Right. It's a sad story. We start to understand a bit more about habitat quality and what advantage it might provide. We really focus on preserving particular areas of high value. So the western side of the slope to down, the eastern side might be good. The National Parks wants to prioritise its management of areas that the new one is looking at ground and these kinds of things. Private companies that demand environmental conservation have this information in there, and that's good choices about what areas are likely to see sensibility.
Can I just ask you, are there any artificial ways of providing some habitat?
People have tried it, but it's the scale that's the problem. People put out water, these areas, some but the maintaining those kinds of resources, obviously put up shade and water holes and things. But really, it's a big notion of massive tracts, 1 million hectares, and how many birds can you save? I don't personally think it's good. And everything helps in keeping birds in the landscape. If you're talking about persistence in around species to stay in the landscape.
So if you had more money, what direction would your research go?
Well, I'm interested in applying what we know now to conservation practice. So talking to people like the Australian landscape, if they have areas to regenerate, how do they do that? Which species are important? How do we manage our burning patterns and birds across the habitation? which areas are absolutely critical for the habitat to be maintained. Those kinds of questions. Life-saving shelter, I think it's really crucial. But that's where I want to go with this work. It would be nice to keep doing more research. That would be great. Different species. But I think, to me, this is reasonably controlled. We're looking at the problem. It's based on lots of species all at once. I think it applies on this in nature talking to land managers, conservation agencies that is the best approach from my point of view.
So, for instance, AWC have done quite a bit in terms of fire management. In other words, trying to avoid these hot fires late in the season and doing some of this spot burning early. And that seems to have certainly some effect on some birds and some mammals, in that not all the food disappears, and some birds and some animals can survive. That's, yeah.
I think that's the key, keeping animals in balance, so we can sites from the channels and move back into areas as they come.
Going over there to answer the questions.
So, okay, you have to come over here.
Oh,
Okay, so in terms of, you said,
You have to go your way.
oh, okay, we'll both have to come in. Okay, so you did say that the birds increase their body weight when the temperatures go down. I assume that's because the insects must be more active and they must increase their feeding during that time. Is that right or not?
it's possibly true, yes, but it's also that they're not losing water at the same extent. They're not dehydrating. So
Okay.
they eat, they put the water, their body water pool is replenished,
Okay.
so they don't then lose water. But what you see on these really hot days, so we've been doing watches throughout the day to see what they do when. They seem to anticipate a hot day and they go mad foraging first thing in the morning, and they just dash in here and there, and they spend several hours just totally obsessed with foraging. And you don't see it on any other day, only on these hot mornings that they put a lot of effort into foraging, bringing up their water budgets, we assume, water pools.
So is that barometric pressure effect or?
How do they know? I don't know how they know.
No, I mean, there must
Yeah.
be some point.
Yes, one. I mean, it's a reasonable assumption, I'm sure.
Does anybody have any? Yes.
Yeah. Yeah. Well, they might be. They might be.
The question was, can you train birds to breed at different times of the year?
No, you can't train them to breed at different times of the year, but they may be advancing their breeding, and a lot of birds are. They're breeding earlier as spring temperatures warm, and that tends to be because there's more food available earlier in the season than there's previously been. The problem with the arid zone is that food availability is strongly tied to rainfall. So if temperatures increasing and rainfall is declining, you're probably not going to see earlier breeding. So that's the obvious way birds might or one way they might deal with these rising temperatures, but I have my doubts whether they'll be able to do it in the arid zone, or do it effectively in the arid zone.
Great.
You said earlier that little jackies get the food in the hot weather. Put any water out.
We did, yeah. They kind of dance around it and they look at it and they're not sure, and then they poke their whole head in and then they pull their head out and they splutter and carry on. So they don't regularly drink. We concluded that. So the honey eaters will come in, they're just immediately drinking, and the Jackie Winters are watching them and follow suit. But you can tell it's not something they do regularly. But yes, they will take water in those conditions.
I noticed that showed us the Jackie winters out in the open on the branches, brooding.
Yeah.
Is this their normal methodology of brooding? There's no shade.
That's right. So those nests tend to be earlier in the season when they actually like to get sun on the nest. But they don't get it right all the time. And we think it's because they're not used to these extremely hot days. They don't know how to deal with them. So the other thing they do, which suggests that is that it's unusual, is that once the eggs die, they continue to sit on them and incubate them right through to the time they hatch. So they waste all this time sitting on dead eggs. And so we think that this is a new phenomenon for them. They're not equipped to deal with these kind of hot temperatures. But this is what our current honours students working on. So we're looking at how much the habitat is important at the nest in terms of the effects on chick survival and the effects on parental weight loss. So there's a lot of variation in where they choose to site the nest. And the work we've done so far suggests they actually site a nest so that it gets sunshine in the morning, when it's very advantageous for the female to be sitting there and warming up herself. Then the male has to feed her much less. But so at the same time as they choose a site where they get the sun in the morning, it's a site where they don't get the sun in the afternoon. So they seem to be able to actually predict where the nest will be in a best position to take the advantage of cold and warm.
They are smart.
They're very smart. They're really smart.
They can't control
No, they don't seem to be able to deal with them. So it suggests it's a new phenomenon. So their behaviour is quite plastic until you get to this hot end of the range. So we're assuming it's because they simply haven't experienced it in their history. Yeah.
Is it possible that the survivors would be right into conditions?
Possible, because they do learn. Whether it'll be enough, whether it'll be fast enough, is the question.
What's the lifespan?
Probably 15 years at maximum, probably 5 on average, maybe less. So if you make it to recruitment, then you tend to survive reasonably well. It's that first year where survival is or mortality is quite high. But yeah, I mean, yes, they learn and they learn fast. So once you habituate the adults, the chicks learn immediately, their own chicks, and they're habituated for the next breeding season. So it's a good return on investment from our point of view. So they learn quickly, but whether they can develop strategies that can deal with these extremes, I really doubt it.
Yes.
Yeah, it's body temperature is about 40 degrees, so they run hotter than humans, but yeah, slightly higher. So yes, they must maintain their body temperature like humans, like endotherms, in this very narrow temperature range. And if they don't, then they pay the cost of extra energy and water to maintain homeostasis. So when it's hot, when it's cold, they use more energy, but when it's hot, they use more energy and they evaporate water. So it's harder to deal with the hot than it is to deal with the cold, more than likely, in terms of their homeostasis.
Right. Is there anybody online who'd like to ask a question? Yeah. Okay. You have to unmute yourself. Oh, hang on, just a minute. No.
I think you can. Who wants to ask a question?
Does anybody want to ask a question? Can they hear us? I assume they can.
Another 10,
Yes, I know. We can't see them.
Put messages on the chat.
Yeah. Okay.
no, those are people who can't hear.
Oh, okay.
So do you want to work this?
I don't know.
I'll leave it to you.
John Rawson wants to know whether you're finding that the breeding season's starting earlier.
We haven't been out there long enough to know. It started earlier this past year, but that was probably related to rainfall. So we had like we had here, a very mild, wet summer, spring and summer. So the birds started breeding earlier. But whether that's a trend over time, we don't know. We simply haven't been out there long enough.
That's the only
Okay. All right. Well.